Okay, so in the last class we have seen the object-oriented programming, but now in this session we would be moving from object-oriented programming to grand overview of machine learning. So I won't get into the details. I would just give you the overview of what machine learning is, what are the tools available, what is the ecosystem, and then you'd have the opportunity to get into the details because there are subsequent classes and it would be um, taught by a very good researcher. So he would be walking you through all um, uh, mm, the details of how the machine learning is done, the theoretical details, and the state-of-the-art techniques. This session is just to facilitate a smooth transition uh, from um, the thing that we have been studying so far to the next step. So let us start this creating a class. You can see that I have written custom data type with magic method. So what is magic method? We would study a few magic methods today. Magic method is sometimes you have seen, for example, I mean, what I can say, something like this. Okay, this window is interfering with my VS Code. Yeah, let me shrink it. Yes. So we would see the magic method, and we would gradually get into the intricacies of object-oriented programming, the advanced details, because we have taken a look at the fundamentals. So right now we are building a custom data type, a complex number. So we are building a complex class that represents a complex number with real and imaginary parts. Why it is difficult? It's difficult because, if you try to create two complex number, x equal to a plus ib and y equal to, so I'm in the coding cell, that's why it is giving this kind of problem. So x equal to a plus ib and y equal to c plus id. Now if you create this kind of data type, then if you add x plus y, then if you add x plus y and keep it in the z, so the addition should follow this kind of order. A plus b should be added, and then after I times, I would say c plus, no, b plus d, b plus d. This kind of, it's a different kind of addition. It's not like, for example, u equal to 50 and then w equal to 60. So what would be maybe y or p equal to u plus w is 50 plus 60, no issues here. But when we are adding a complex numbers, we have a different issue because the addition is not happening in the usual sense. So we need custom data type. That is the motivation. We need custom data type. And that's why our custom data type would look something like this. So no issues till here. We don't have any issues here till here because we have seen this kind of construct. So when we are initializing this object, we are passing real equal to 2, and real is getting this value 2. We are passing imaginary equal to 4. Imaginary is getting value 4, and they are assigned to the self.real, self.imaginary. These are the attributes. So the attributes are getting this number. That's fine. So if we if we till then, I mean, if we execute this class and if we execute this class, we would get this kind of values. That's fine. But what about the additions that I have told you about? To get this addition, we need something called magic method. What is this magic method? Magic methods are, for example, you are seeing, by this time you are seeing this double underscore init double underscore. So this kind of construction where double underscore precedes a name and again double underscore succeeds the name, they are called magic methods. They are also called dunder methods. What is dunder? So dunder, for example, dunder methods or magic methods, they're same. So why dunder? Dunder because double underscore. So this double under, that's why they are called dunder. D under, double under. That's why often they are called dunder methods. Dunder methods or magic methods, they are the same. But these dunder methods have a specific purpose in this kind of operation. So we would see the addition, how the addition can be changed with the use of this special dunder method. So you cannot create a dunder method out of thin air. It is not possible. Python has specific dunder methods and you have to use them. For example, this kind of plus, this kind of complex number addition, how you can assign different meaning of addition to your custom data type. So this addition is a custom addition. How can you create a different type of addition, override the current addition, the usual addition that we do with this dunder method add. So the thing is, when a complex number is added with the right side, so y is the right side, so the x plus, this plus is associated with the x, so this plus is associated with x. When y comes in the right side, that y is called right, that y is called right. And self.real is the x plus, because plus is associated with the left hand side. So x is the self.real plus right means y in our case dot real. So see how this addition is taking place. So a plus b is x dot real y dot real plus y dot real. So this is the left hand side real, this is the right hand side real, and then similarly this is the left hand side imaginary, this is the right hand side imaginary. So what would happen is this, when you do this kind of operation, then this plus would follow this methodology or this kind of I would say custom function. That is the use of the dunder method. But the game is not over. The game is not over. It's not simple addition of the real part and the corresponding imaginary part. You need to return the same data type, this same data type complex. You need to return the same data type. Otherwise how could z would get the same data type as of x and y. X and y, they are getting added, and z would be the same data type. They would it would carry the same connotation, right? So that would only happen when, if you follow the addition and then return back this complex number to this this quantity, the left hand side z quantity. So z gets this complex number. And if you print dot z dot real z dot imaginary, you get the same thing. For example, let us execute it. Let us execute it, and it will remain the same. There is nothing that has changed in this. But when you execute this, you get 7 and 3, because 2 plus 5 is 7 and 4 minus 1 equal to 3. So we get this. So this is the way you change the complex number, the addition operator of the complex number. What would happen if you do something like, so this operator? What would happen if you do this kind of operation? So this kind of operation also is supported. And to do that, it is called the, I would say, the increment operator. So in that case, the construct, I mean, by this time, the construct would be clear to you. If you use the right, then because this is appearing on the right side, right? So right dot real is getting added with the real, and imaginary getting added with the real. So these are the two operators. That is the beauty of this thing. Plus is one operator, and maybe z or even x, y. So that means x is getting added. I mean, x is incremented by y. This is the meaning. But we are using this kind of special operator, and to empower our data type to use this kind of operator, we need to define it. We need to define how. We need to use a different kind of Dunder method, that is I add. If you use I add, then this kind of operation is possible, and it follows the same logic that I have explained before. So I need to move a little fast. So if you follow this, it would be clear to you the second part, and I will be coming to your question, and just hold on. So the thing is that this kind of Dunder method, it's not that um, uh, these are only created by you, the user. This kind of methods are inbuilt in Python. For example, if you have two strings, hello world, and when you are adding two strings, these are not the numbers. But Plus knows that when I'm asked, when the left hand side and right hand side both are strings, when I'm asked to do addition here means concatenation. And when this concatenation takes place, actually under the hood, this Dunder method is called. It's the same like this. If you follow this kind of addition here, you can play with this. In Google Colab, you can spin off your the notebook, and you can do the same thing with x dot add y, and you would get this x plus y, the same thing. So here too, I mean, this hello and world, they are concatenated with this plus. The plus, since it is overloaded like this, we call it overloading. Since it is overloaded like this, under the hood, it calls this double underscore add double underscore, and they get concatenated. So this is how you create custom data type. Why I'm teaching you this? Because when you have started learning Python, what kind of data types you have learned? You have learned integer, float, boolean, and then what kind of data structure you have learned? These are the data types. What kind of data structures you have learned? List, tuple, set, dictionary. But now you are getting senior. You are gathering experience. You are gathering more and more professional experience in Python. So you are now creating your own data types. This is how you create your own data types, by creating classes, and you add your own methodologies. You add your own functionalities through the Dunder methods. You empower your data types. So this is a classic way of creating your own data types. Now you are creating your own data types. And the last thing I would show you is how you can create a currency data type. For example, currency zero, I mean, these are the two currencies, maybe 13 0 rupees, 13 pairs, something like this. And then, I mean, these are the bills in different currencies. I mean, if you think of a different currency, these would be the bills, and these would be the equivalent of paisa, our equivalent of paisa. So this 100 and 13. So the two currencies, if we create this kind of two currencies, how shall we do this kind of comparisons? How can we do this kind of comparisons? I have shown you doing addition, I add, but I didn't show you doing comparisons. For example, greater than, less than, greater equal to. Since like complex number, there are also two quantities. It is not straightforward to do this kind of comparison. So we need to write these functions. Again, Dunder methods. Going back to the Dunder methods, we can, sorry, when we are invoking this class, sorry, this instance, when we are invoking this instance, so this is simple. This, you know, this some bills and coins. Sorry, I forgot the word coins. The bills and then equivalent of size coins. So the if you pass these values here, the bills and coins, these attributes should be set up. No issues there. We know how to set up our attribute because the init constructor is calling them. But, and this is the getter, I guess, yeah, getter function that is returning the total amount that you have in your in this currency. Maybe it's an account, so it's giving you the total amount that you have. But when we are using this double underscore GT double underscore, it means greater than, because under this function, I mean within this function, we are actually implementing greater than, and within this function we are implementing greater than equal to. So the right that we have written, here, I'm using a different word. You can use right, there is no issue, but just to show you that it doesn't depend on the word. Rather, you can write anything you want, but it makes sense if you use some meaningful word. So I've used other. Other means the right hand side. The right hand side, for example, this is the left hand side, this is the right hand side. When the right hand side is passed here, we are, so this is the self means the left hand side. So INR1 greater than equal to, this is the left hand side, self, and this is the right hand side. And this right hand side, so this is the getter function. Getter function is giving you the total amount. So is it greater than equal to, or is it less than equal to? So all these Dunder functions are actually incorporating, they are running under the hood this kind of operators. So this is absolutely possible when you execute them. This is absolutely possible. True, false, all these things are possible, right? So this is the beauty of Dunder methods, and Python has a lot of them. For example, if you, I mean, at some point of time, you start writing the PyTorch code for deep learning. There we often use this kind of operation, or even for string. I mean, if you, my name, my is a city equal to Kolkata, and if you print ln city, so this is the number of characters here. But if you print dir city, so it would give you all the Dunder methods and also special type of methods that this object, the string object, has. Now you can see this alien. So when we are writing alien, of city, we are getting 7. But at the same time, when we are writing Kolkata, Delhi, Chennai, and then we are writing alien, then also it is giving correct answer. Different data types, same result. Different data types, same result. So that is what the classes, I mean, should be, right? That is how the classes should be. We want to add things, and we want to add things means they would know that what addition means. In case of strings, they would concatenate. In case of complex number, they would add the real parts and the imaginary parts. So same interface, different attributes. So same interface, different attributes. What did I say? This kind of characteristics. It's one of the three pillars of object-oriented programming, right? Same interface, different characteristics. So they are behaving in the same way. The try to understand. This is a string. It is giving you the length of the sequence, the number of characters present. When it is the list, it is giving you the number of elements present. So when the alien is called under the hood, this function gets called, and it knows under the hood, it knows what kind of data structure or data type I'm dealing with, and I would operate that way. So for string, it is computing the number of characters. For list, it is computing the number of elements. So same interface, different characteristics. This is the polymorphism. So Dunder methods, what they do under the hood, they do the polymorphism. So city is the string and cities is the list. But what is happening is, this is what is happening. City is calling this, and cities is calling this. That's why when you're writing alien, this details is abstracted away from you. These details is abstracted away from you, and you are not required to be overwhelmed with all these details. This is the beauty of polymorphism. This is what we have just seen. Before going into the next step, let me see if we have any question. So there are questions. Oh yeah, glad that you are paying attention. That would be A plus C. Okay, let me correct. Let me correct it. It would be, is that A plus C, right, right. A plus C, B plus D, and that will be B plus D, right? Absolutely right. Amit and Shantani, they are absolutely right. Shoroditya sir, why is X being called self? So that's how the plus sign that is getting associated with the left hand side, and the left hand side is actually calling the that Dunder method, and since the left hand side is calling, X is calling himself, so X is passing himself. So remember when we talked about this what is self, we said that the instance is actually passed through self. So here X is passed through self because X is on the left hand side. Sir, could you please repeat this part? So Devtirthe. So if you please let me know which part I need to repeat. I would definitely do that. No worries. Just let me know which part. Sorry, I missed your question at that point of time. I was in a flow, so I was completing that. Sir, sir, n can be used between them. /n, the new line character. Not sure what does that mean. Anyway, Lakshman Soni, sir, is it necessary to use self for a left value? Since it is calling the Dunder method, so it needs to pass itself, right? That's why maybe, yes, perhaps you are talking about this thing. So yes, so it's passing itself. There has to be placeholder for x, otherwise how x would add its real and imaginary part? X real and imaginary part have to be there. The last line that you wrote between city and cities. Okay, I'm coming to your question, Pearl. But let me first answer Lakshman. So this is one thing. Does dir city tells us about all dunder? Yes, not only all dunder. Yes, definitely you would get all dunder. In addition to dunder methods, whatever methods are defined within this class. For example, when I am, so city is, what is city? City is the string. And when I am applying dir over city, when I am applying dir over a string, not only the dunder methods, the other methods like, I mean, upper, title is, if this Kolkata, I've written all of them in lowercase, but the first letter should be uppercase because it's a proper noun, right? So if you use title, the first letter would be uppercase. So these methods are not dunder methods. They're the usual methods. So dir lists all the dunder methods as well as those methods which are not dunder, the usual methods. So I clicked on uh, the scrolling button on VS Code, and I'm now seeing all the methods that string has, all the methods. So these are non-dunder methods, these are the dunder methods. So you get all of them. The last line that you wrote between city and cities. So slash n can be used between them. I mean, yeah, maybe you are trying to say different lines, something like this. So if I write this way, I get 7 and 3. Not sure if I understand, but whatever. So I'm done with this. And the next thing is a very important question and very, very difficult question too. For example, I have written this divide function. It's a very harmless looking function, divide a and b, and I'm dividing a and b. But it has a problem. What happens if b becomes 0? So we are not zero guarding this function. And suppose this function, this divide function, is not just a single line function. It has got thousands of lines. Maybe a function having thousands of lines is not a good function. You need to break it up. Maybe not 1,000, maybe 40 or 50 lines. Okay. And now, after writing so many 40 or 50 lines of functions, maybe 100,000 of this kind of functions, your partner has shown you that there is a glitch. You need to fix that bug. And doing it for one function may be okay, but if there are, maybe you have found out this kind of bugs, maybe 20 or 30 functions, and you need to check all these files, you need to edit them, and you need to test them, you need to run them and see if this new edit, the fixing the bug, is I mean, if this is happening smoothly, or this kind of fixing this bug is manifesting into some kind of a different error somewhere else. So all these things would be difficult for you, right? I mean, so how we can do this? How we can do this in a scalable way, in an efficient way, and very fast without editing this function? We won't be editing this function. So if there are hundreds of lines of the codes in a function and you are trying to edit them, it would be horrendous, right? So the problem is you cannot edit this function, but you need to add zero guard to this. How you can do that? So this kind of thing is called inner function or closure, I don't know, closure maybe. So inner function, a function that returns function. So we have, yeah, I'm coming to that. Yeah, you're right, Deep Kumar Majumdar, you're right. I'm coming to that. Hold on. So the function that returns a function, what happens is that, look, what I did is I have written a wrapper that's called ZeroGuard. I have named it a wrapper, and I'm assuming that I told you function is an object. I can store function in an array. I can pass function to another function as an argument. I can do anything I can with objects. That I mean, I can do with function anything that I can do with any kind of objects. So that's why I can pass divide. I can pass divides as an argument to this function. So this func, this function is nothing but this divide passed as an argument. So what ZeroGuard does is that it receives this function as argument and it returns this function. So this function is written as an inner function inside the function. So we have defined a function inside a function. That's why it is called an inner function. So that's why it is called inner function. Inner function. Inner functions. Inner function is defined within this outer function. We don't call it outer function. We don't call it outer function. That's why I'm removing it. We call it wrapper kind of. I mean, the outer, or maybe the wrapper function is the right word, but since I have used wrapper inside, let us not call any function. I would say it is a calling function, but this is definitely called inner function. So this inner function, what it does is that this inner function takes two arguments, and here we are doing the zero guarding. We are checking if b equal to 0 or not. If b equal to 0, we return, we don't stay here, we return from this, we return the control. If b is not 0, then we call the function that we are passing. So this way we're guarding. First, we are checking if b equal to 0. If b is not equal to 0, we are calling function a and b, and we are returning the value, the return value that it supplies, the divide function supplies. So what is actually happening is that when you are calling this function, you are getting an enhanced version of divide. Enhanced version. The enhancement is happening here. Enhancement is happening here. And this function is called at the last line of this enhanced function. I mean, think of this slowly. You'd get how the control is happening, and it would be clear to you. So this is nothing but, I mean, if I call this thing, for example, divide equal to zero guard divide, then this divide would be the zero guarded function. This divide would be the zero guarded function. But there is a better way of writing this thing. The better way of writing this thing, I mean, all I've said that would happen if I write this thing, and if I now say 3 comma 0, it won't divide, because this thing would be now kicking in and it would be checked, because this divide is an enhanced function now. But we don't need this thing. We have a better way of doing these things, that is called a decorator. Decorator is what its name signifies. It decorates. The thing I was saying, it enhances. Python doesn't use the word enhance. Python use decorates. Decorate means this function name, if you prepend with at sign, this ampersand sign with this, and if you write on top of that, it is exactly like this. It is exactly like this line. That means you have decorated this function or enhanced this function. And in this situation, if you execute this, see, this thing got divided correctly, but when you are supplying 0, it didn't get through. This thing guarded the zero division. So why we need decorator? Decorator has lot of use, but the interesting part is that there is something called data class. Data class is heavily used in numerical computing, deep learning, and stuff like that. So I'm explaining all these things just to introduce you to data class. So consider this example. What would happen if we write a point class? A point class. A point class is something, it's not classic, point class. A point class is something like this, two-dimensional data, X and Y. We do this way. But it would be better, I mean, if you execute this, it would be like the usual point class. And this dunder function, this is again a new dunder function, and its application is this. When you print a class, this function would get called. This is the application. So different dunder function has different application. So this magic method or dunder function, it gets called when you print a class. Nice, right? So now we are going to read this data class that I told you. Data class is a decorator that if you create a class this way and put them under data class, then you get something similar, but you get actually a lot of other functionalities too. For example, let us create a point, but not in this way, but in this way. Definitely you have to write a lot less now. You are not becoming so verbose. You are writing a lot less now. But at the same time, you are getting a lot of functionalities. For example, you define a point this way, but this kind of overloading, point is two-dimensional data, X and Y, this kind of overloading, which otherwise you would have to do with this kind of dunder method, now it is, I mean, available free of cost. Free of cost means data class has already implemented this for you. And now you can compare P1 and P2. You don't have to define that. Data class already gives this facility to you. There are a lot of other things data class gives. For example, order. If you write this way and you define a person this way, you can sort them over their age, and then over their name in alphabetic way. So it gives you this feature. Just declaring data class as a decorator over your class. So let me stop here. This is how you can create custom data types. This is the data class that you would be using in future. So I just made the transition between the data type, so the object-oriented programming and the custom data type. So there are a lot of dunder methods, whatever data types you have learned. For example, you have learned integer, float, Boolean. These are the data types you have learned. The data structure is list, set, and dictionary, all these things. Your homework would be go to them and check with the dunder method, dir, maybe list, and you'd get to know what are the dunder methods are defined as part of this class, what are the usual methods, non-dunder methods are defined, and your objective would be to use them. And I would start, I would recommend starting with the string class. String class is actually very rich with a lot of utilities. There are a lot of utilities in string class. For example, this my name, if I use this string class and I use title, what would happen? So see the M, maybe here I'm writing my name, Sujoy, and so, or maybe let me see if space works. The space, yeah, space works. So the first letter of every word is capitalized. So that is the use of title, and title is title is non-dunder method for string, and there are dunder methods too, dunder methods, non-dunder methods. So everything, for example, everything that is there, dir, maybe this kind of thing, everything that is there, it's worth taking a look and use them. For example, so many things are there. Strip I use a lot, then split I use a lot for list though. L strip, R strip, left left side strip, right hand side strip, is title, is space, checking, replace. These are widely used. So your objective would be to, I mean, your homework would be to studying them in details in your Google Colab. So with this, I'm completing the pending stuff that I had in my last session. I was supposed to complete this, but with this, our journey of object-oriented programming within this very short time is complete. What I tried doing here is not teaching you everything about object-oriented programming, but I mean, um, sparking the curiosity so that now you are able to get going with the object-oriented programming and how it is related to the numerical computing or the data science through this data class and this kind of constructs, how it is doable. Any question? Or otherwise, we would go to the next step, that is the machine learning overview. Starts. So now we are moving to an exciting field of computational science. You would take a look at the machine learning, what it is. Let me share my slide. Okay, I guess now you would be able to see machine learning. Okay. So you must have seen this slide. There's the project life cycle, data science project life cycle. Please let me know if you have any question in this part, or even if you have any question related to the previous part, let me know. So this is the project life cycle, and you have already seen that you are familiar with this. Today, we would be spending time in this part of this entire project life cycle, that is the model training, model choosing, or the modeling part, how we would be doing the modeling part. So let us take a look. So machine learning consists of broadly consists of these three different tasks: supervised learning, unsupervised learning, reinforcement learning. So supervised learning, what is supervised learning? Supervised learning means when the data comes with the labels, targets. What is data? What is labels, targets? I would be coming to that. Unsupervised learning is there is no target or label, and reinforcement learning is something that is out of the present scope. We won't be going into the reinforcement learning. Next, within the supervised learning, there is something very important task that is widely used, that is called regression, and another is classification. Within the unsupervised learning, there is clustering and dimensionality reduction. I would like to tell you that within the supervised learning, unsupervised learning, there are a lot of other things too. I mean, as the field is moving ahead, a lot of new things are coming up. The research is making progress, and we are coming to know a lot of exciting stuff. So the field is evolving. So there is semi-supervised learning, there is weekly supervised learning. All these things, they are coming on the right hand side with the more and more branching of the trees. But for you, it is important to know the basics. These are the fundamentals. So supervised learning has got regression and classification. Unsupervised learning has got clustering and dimensionality reduction. Don't get scared by all this mathematical stuff. I would be explaining you everything. So, but I did it in a rush. So please let me know if you can see any typo. If I start explaining to all these things, I mean, explaining all these things to you, you'd be I mean, getting clear picture of what they mean, and then probably you can find any typo if there is any typo. Okay, so the next thing is, let us take a look at regression. What is regression? Regression is, consider this data type, the data set. We have a factory machine, this machine when it is moving. So since it has a rotor part, it rotates, and we can check how many revolution, the full rotation, I would say, per minute has happened. Okay, we can check it with there is a sensor for all these things. So using this sensor, we can measure this rotation per minute or rotation per second, whatever the unit. Another is vibration, how much it is vibrating. So this rotation per minute and vibration, they are some strong indicators of the machine health. Suppose we have the machine health recorded here between 0 to 10 scale. Some domain expert is rating this machine health between 0 to 10, and this is uh, I mean, there are a lot of machines, or maybe this machine is health is judged or monitored over a long period of time, and we are getting this kind of machine health data. So the idea is to know how this machine health is related to this kind of data, because if we know the relation, then at certain point of time, if we know the rotation per minute and vibration, we would be able to say that if the machine is going to fail or if the machine is in a sound health. That is the motivation, that's what we want. So for doing that, we need to know how this machine health index is related to rotation per minute and vibration. Now, since these are the things that we have as input, and we are interested in we call them output, we are interested in this output. So these are the I mean, these two columns constitute what we call feature metrics. Feature metrics are independent variable, and this is the dependent variable or the target. We are interested in knowing the target, or we are interested in predicting the target. So X is the feature matrix, and each column is called feature. So this is the X2 and this is X1. This is the first feature column. This is the second feature column. First feature column is vibration. Second feature column is rotation per minute. So this is the two columns constitute our X, and Y is the response or target variable. And we are interested in knowing Y if we are given X. For this data set, we have Y and X, but in future, for example, it may be the scenario we have the RPM and vibration of the new machine, but we don't have the Y. If we know the relationship from this, for that new machine, we would be able to tell how the machine health is. That is the motivation. That is what we are going to do in regression. Why it is called regression? It is called regression because the target variable is continuous. This target variable is continuous. So that's why it is called regression. But there is a different machine learning task. Look, we are calling them machine learning task. These are the machine learning tasks. So this is kind of your template. When you would be doing machine learning, when your boss, your manager, your teacher, when they would be asking you to, when they would be giving you a data set and they would be asking you to do machine learning, your job would be to identify which task to apply to solve your problem. These are the fundamentals. These are the templates. When you get a new thing, you may assign to a particular template, you may use one of them, or if the job is complicated, you may require many of them in sequence, right? So these are the fundamentals. So regression means this Y target variable yi belongs to the real number. So these are the real number. That is the meaning. Yi belongs to the real number for all I, yi belongs to the real number. But there is another thing, classification, where yi doesn't belong to the real number. For example, if this is the situation, we are not interested in machine health. We are interested if the machine is faulty or good. If the machine is faulty or good, integer, faulty can be represented by 0, good can be represented by 1. By the way, there is no question. Maybe you are listening, or maybe I am not audible. Am I audible? You can hear me? Can anybody say yes or no? Or oh, yes. Okay, good, good, good. So the thing is, the machine health, when it is represented by a real number, we call that task regression. When the machine health is represented by something binary, or maybe not binary, maybe in 3 different discrete levels, faulty, good, something in between, 3 classes, but discrete classes, kind of equivalent to integer representation. In that case, we call that machine learning task classification. Look, in both regression and classification, xi means the feature matrix, xi comes with, so xi is a vector here, xi is a vector means 2-dimensional vector. This xi comes with yi. That's why it is called supervised, because there is a target variable present that makes this regression and classification supervised, presence of this target variable. But there is another class of machine learning task where the target variable is not present, So we just have this data, just xi is the data, we have bunch of data, and our objective here would be to discover the structure present in the data. Structure means what are the groups, clusters, groups in the data. Are there 3 groups or are there 4 groups? For example, maybe here, so this is not the thing, pen. So maybe we have this kind of data set, this kind of data set. So here clearly we have one cluster here, one group here, one group here, and there may be these 2 things, they are outlier kind of guy. We have a solid group here, a lot of points are crowding in a small place. I mean, the density is good. We have another group here, but this guy looks like an outlier, or maybe associated with this group, and this is surely an outlier. It doesn't match with the data set. So this kind of structure we recover in this problem statement, the machine learning task, that is called clustering. Sorry, let me erase all. Okay. Okay. So let us take a look at clustering. Clustering means grouping them. So we have all this data set, we would throw away all this data, we would just keep the cluster centroids, the feature vector that would represent the cluster. That means, look, n is the total number, 1, 2, 3, 4, 5, 6, maybe 10 or 12 data points, n, capital N. That capital N is shrinking, so X prime is the cluster. That capital is shrinking, we would get maybe 2 or 3 cluster. So X prime is the cluster. So we would throw away this entire data set, we would keep the cluster center. That is the 2 groups, we would say, or 3 groups. So small n is much less than capital N. That is the objective of clustering. Okay. What is dimensionality reduction? But before that, I see there are questions. How can I move laser pointer? Yes, laser pointer is better. Yes, exactly, Lakshman. You're right. Small n is the number of clusters, or number of groups. Correct. Sir, could you please explain clustering again? Sure, why not? Now the thing is, this laser, I chose laser pointer, but I think it's difficult to control this. Okay. Let me see if I can proceed with laser pointer. I'm not too comfortable, but let me try. So someone wants to know clustering a little bit in details, or maybe once again, I would go through the clustering. Clustering is, we have this data, the bunch of data points. Here, data is two-dimensional. Data is vector. This and this constitute the first data point. 941, 301 constitute the second data point. This way, we have so many data points. 1, 2, 3, 4. These are the data points. I mean, the first data point, second data point, third data point, fourth data point. So this is a particular data point. So n is the number of data points. But as I showed that we want to find clusters, maybe if we plot them over a two-dimensional point xy plane, we could have seen how they are distributed over the plane. And from there, maybe we could have seen that these points are distributed in this fashion, maybe in this fashion. So clearly, we would say in that case, we have three clusters, three groups. So in that case, the small n would be 3. Small n would be 3. What would be the capital N? Capital N is all the rows, number of all the rows. So clustering is to study all these data, the data points, and figure out how many groups are there. So no y, I'm not giving you y, I don't have y. That's why this y-free machine learning task is called clustering. It's unsupervised. It's completely unsupervised. We don't have y. There is another unsupervised machine learning task, that is dimensionality reduction. Let us go to this. So in the earlier case, I showed you this is two-dimensional data. What would happen if it is large dimensional data? For example, the gene sequence that we use in bioinformatics, they come with maybe thousands of values in a single vector. So this kind of data set where capital D is large. So this is the first sequence, gene sequence. This is the second gene sequence. So this is a single vector. This is a single vector. This is a second vector. Now, if D becomes so high, then it is very difficult to visualize. We can plot in 2D, we can plot in 3D, we cannot plot in 4D, 5D. Human perception is limited to 3-dimensional plot. I mean, 3-dimension and 2-dimension. I mean, within 3-dimension, we cannot visualize 4, 5, 6. So sometimes we feel the need to reduce the high dimension D, the capital D, to smaller dimension, small d. And this is the task of dimensionality reduction. Reduce the high dimension to lower dimension so that the data structure is maintained. I mean, the group is maintained, the distance is maintained. If two data point is far away in this original representation, they should remain far away. They shouldn't become closer in the smaller dimension, right? So when we change the representation from the higher dimension to the lower dimension, we also call it, one is dimensionality reduction. One way of calling it dimensionality reduction. The other way of calling it is that the higher dimension is called manifold. Manifold means surface. So it's kind of living on a, I mean, high dimensional representation of a surface, hypersurface. So that is called manifold. In mathematical way, we call it manifold. So higher manifold to lower manifold, or higher dimensional manifold to lower dimensional manifold. So this is the higher dimensional manifold. This is the lower dimensional manifold. Okay. For example, you take a piece of paper. You make arbitrary dots here, right? And then what you do is that you roll the paper. You roll the paper. You roll the paper. So this paper lies in 2D, but this roll, they lie in now in 3D. So if I give you the point coordinates in this position, it would be 3D, x, y, z, x, y, z, three coordinates. You would need three coordinates, x, y, z. You would need three coordinates to specify the points here. But if you somehow have the mathematical tools to bring them to a lower dimension, you'd get exactly their characteristics in two-dimensional, how close or how far they are. It will be easier for you to visualize in two-dimensional. That's how the dimensionality reduction, that is the intuition, physical intuition. That's what is happening. Okay. Any question? No question? So we have taken a look. So let us summarize. Let us summarize. So these are the tasks. Regression. Regression means this. The target variable would be. So supervised learning means we have target variable. Unsupervised learning means we don't have target variable. We would just discover the structure, inherent structure of the data. So in supervised learning, there are two machine learning tasks. One is regression, another is classification. In regression, the y is a continuous variable. In classification, y is discrete variable, kind of equivalent to integer. We can represent them 0, 1, 2, something like this, right? In clustering, we don't have the y. We reduce the number of data points by discovering the groups in the data set. But in dimensionality reduction, see, it's interesting. In clustering, we are actually reducing the number of rows. In dimensionality reduction, we are reducing the number of columns. Don't forget it. It's a way of visualizing maths, right? This is how you visualize maths. So in clustering, you are reducing the number of rows. In dimensionality reduction, you are reducing the number of columns. The columns are the dimensions. But the underlying assumption is here the vectors are row vectors. If it is column vectors, then it would, the interpretation would be swapped. In that case, if it is a column vector, you would have to reduce the number of columns in clustering, reduce the number of rows in dimension reduction. But now we are considering the row vectors. These are the row vectors. All these are the row vectors. The row vectors. All these are the row vectors. So the dimensionality reduction means reducing the number of columns, and clustering means reducing the number of rows. Okay, I guess it is clear now. If it is not clear, let me know. So these are the machine learning tasks. When we talk about the machine learning tasks, in the first hierarchy, there is supervised learning, unsupervised learning, reinforcement learning. We won't talk about reinforcement learning here out of the scope. We would talk about supervised learning and unsupervised learning. Supervised learning because target variable is present. Unsupervised learning, target variable is not present. Supervised learning is regression. We call it regression when target variable is continuous. We call it classification when target variable is discrete. We call unsupervised learning clustering when we are discovering groups or clusters. We call unsupervised learning dimensionality reduction when the task is reducing the dimension. I showed you the analogy of putting points in a sheet of paper and then rolling it. When you roll it, you go to the 3D and flatten it. You would return back to 2D. That's how that dimensions talk to them. And think of this, our biologist friends, they deal with maybe thousands, maybe they deal with feature vectors which live in a 1,000-dimensional space. So how big or how large dimensional that would be? It's very difficult to visualize them. They need to do this lower dimensional projection. Okay, before moving in, let me see. Okay, I would move a little faster from here because things would become a little bit mathematical. Those who are not familiar with the mathematical stuff, ignore this. I would be going into the coding. If you are a coder, you can understand it intuitively. So I have designed my lecture in such a way that everyone has something of his or her own interest. So if you are not mathematically inclined, it's okay. Go to the code. Your job is to solve the problem. So go to the code. If you appreciate maths, if you want to go get into the maths, then I have things for you too. But before that, let me check. Not unwanted columns. I mean, here things are little bit tricky. I would say which columns we are removing. So it's a deep question. It doesn't have a very simple answer. So which columns we are removing that we may not be certain about. Actually, let me answer your. So it's a beautiful question, Lakshman Soni. So let me answer this way. The lower dimension that I'm getting, it's not that I'm removing fifth column or sixth column, something like that. The lower dimension I'm getting, it is a combination, some sort of combination of all these columns, all the original columns. It is not that I'm removing the first column, second column, third column, and the remaining columns are more important. It is the combination, some sort of combination of these columns that is giving you a richer lower dimensional representation. This is one way of thinking, but research has made progress. We have gone into that kind of dimension reduction too, perhaps in a different way, where we are able to remove some sort of, some unique columns, maybe third column or fifth column or seventh column, but those kind of dimensional reduction techniques are not very widely used. Those are very application specific. Most of the dimensional reduction techniques, the lower dimensional representation is kind of some kind of combination of all the columns. That is the way to put it. So it is not that I am removing some specific columns. In the other way, the columns I'm getting, they are some kind of combination of the original columns that were present. Okay. So I wish I could go into the maths, because if I showed you the math, it would have been easier for you. But within these 2 hours, it's not possible to show all the machine learning tasks and maths and coding, all these things. But if you're interested, maybe this kind of thing, when you would like to go into the maths and see stuff in details, maybe the online journal club is more suited for this kind of thing. If you ask me question, I would be able to show you. Maybe that would require time. We need to set up a one-on-one meeting, but those are the things that can be handled there. So yeah, thank you for this question. Lovely question. So regression, mathematical, but don't worry. If you don't like maths, it's okay. We would go into codes very soon. So the idea is, I told you the idea is to get y from x. X is the feature matrix, the RPM and vibration. I augmented one, that is the bias term. If you at some point of your career, if you fit a line through some xy points, you know y equal to mx plus c. So c refers to the augmented part. So ignore this if you are not interested in knowing all this, but we have this augmented column to take care of that. So this is the feature. So we augment the feature matrix this way. These are the two feature columns, and our interest is to predict y. So how can I do that? How can we do that? So usually the way we can do that, we imagine some sort of functional relation between this x and y. This functional relation can be different way. For example, I take a tangent of this and I take a log of this. I somehow combine them in a weird way, feed some exponent, these and that. I do all kind of weird mathematics that I know, and I try to infer y. That is one thing. The other thing is just simple linear combination W2, W1, W0. So this is the matrix, and the matrix is multiplied by a vector. So when a vector is post multiplied with a matrix, then W2 gets multiplied with the first column, W1 gets multiplied with the second column, W0 gets multiplied with the last column, and all the columns get added up to give you a column. So when a vector is post multiplied, we get a column vector. When a vector is pre-multiplied, we get a row vector. So that is the row space. Same thing, similar thing happens there. Not same thing, similar thing happens there. We get the linear combination of the rows when the vector is pre-multiplied. When a vector is post-multiplied, we get the linear combination of columns. Why linear combination? Because W2 is multiplied with the first, W1 with the second, W0 with the last column, and all the columns are added up to give you a column vector. That column vector I have written with yi hat. Why yi hat is, for example, this vector, when it is multiplied with this vector, it would give you a scalar quantity. You know, vector inner product, I mean x. So this is the transpose of a column vector. When it is multiplied with this, we get a scalar product, and this scalar product is, I'm saying that this is the prediction. Prediction means estimate of yi. I cannot exactly predict yi. We cannot do that. We don't know the world. We don't know the oracle. So we can make a close approximation. Approximation is maybe the right word, but in statistical jargon, we call it estimate. So yi hat is the estimate. So what is our objective? Our objective is to take yi hat as close as yi. Ideally, this has to be 0. If this is 0, then we are the happiest person, because we have predicted yi with 0 error. There is no error. How can we do that? How can we do that? Note here, all these data are given. We cannot change this data. This data is given. Y is also given because it is the health meter of the machine. 1.8, 1.6, this data is given, this data is given. What is not given is these parameters. These parameters are not given. We would set these parameters in such a way, again I am repeating, we would set these parameters in such a way that yi hat would be as close as possible to yi. That is the idea of this maths. So W is unknown. W is unknown. So this leads us to this optimization problem, that we would take xw is when you multiply x with w, is xw. We would take xw as close as possible to y. Note this xw is the column vector. So this is the column vector xw, and y is this y is this y. So y is again a column vector. So when I'm doing minus, so the first term is minus the first term of this column, second term minus second term of this column, and this part, the norm square part, means sum of square. You squared them, you squared the subtraction, you square them and then add them up all. So sum of square. You need to reduce that sum of square with respect to W. You need to choose W in such a way that sum of square is reduced. Sum of square reduced means we have taken yi hat, our estimate or our prediction, close to yi, close to yi. That is the interpretation. That's how we solve regression. That's how we solve regression. And this, what do we call these things? What do we call these things? We call these things our loss function. Never forget this. We call these things our loss function. Loss function is minimized with respect to W. That's how we get optimal W. Optimal in what sense? Optimal in this loss function sense. The name of this loss function is least square. So optimal W, the W we get from this is optimal in least square sense in this. When vector is post multiplied, linear combination is a column vector. Yes, when vector is post multiplied, when vector appears after the matrix, so the matrix columns are linearly combined. So it's the sir, can you again one by one. So when a vector is post multiplied, we get the column vector. And when a vector is pre-multiplied, when you multiply a vector, I mean, when the vector appears before the matrix, that vector is not a column vector, that vector becomes row vector. So when a vector is pre-multiplied, that vector becomes row vector. When a vector is post-multiplied, that vector becomes column vector. And do this, you would understand that in pre-multiplication, we would get row vector. In post-multiplication, we get column vector. Sir, can you kindly explain why we need augmented column and why we choose first in that column? So it's to set the bias, the bias term. The hyperplane that is fitting, that you are fitting, how far would be from the origin? If the column vector is 0, it would go through the origin. If you set a column vector, then you can let it pass far away from the origin. That is the idea. If your point distribution is far away from the origin, then the hyperplane that you are fitting shouldn't go through the origin, right? And the augmented column would take care of that. Shorodipto. Sir, can W be chosen by Gaussian process or it just for supervised learning? Gaussian process, Gaussian elimination or Gaussian process? Gaussian process is a different kind of thing. That's a supervised learning. There is a classifier, so I'm confused. What you are meaning? And again, sir, does the loss function tell us about error? Yes, exactly. This is the error. But how the errors are put in? Errors are put in sum of square error. This loss function, this least square is the sum of square error. So that's why it is called least square error. Okay. Okay, I need to move faster. So this is the mathematical way of solving. I solved that W star. So W I solved here. I solved this. Only regression, this kind of regression allows you to solve it in a closed form. But if you move to classification and stuff like that, you don't have this closed form solution. You need to do with gradient descent. So this is how you solve it, gradient descent. I won't be able to do that. The next lecture would take care of all these things. But the idea is, you after doing xw is the column vector. This column vector is the xw. We need to take xw, I mean the y hat, as close as possible to y with respect to w, and we do that by minimizing this with respect to w. Once we get w, that is our optimal w, and this is machine learning. What we are learning? We are learning w. This is machine learning. By machine learning, we mean learning the parameters. In machine learning, the learning actually refers to determining w. we are learning W. That is why it is called machine learning. Learning means we are learning W. W is unknown. Why we are learning W? What is the objective? Objective is to take the prediction as close as possible to the real target. So we say in a different way. We say slightly in a technically we say it a little bit different way. We say W is optimal in least square sense, or W is optimal in the objective, the loss function sense. So it is optimal in the loss function sense. So instead of this loss function, you can come up with a different loss function. So this kind of loss function is very good to address overfitting. So I won't go into overfitting. You get to know all these things. So loss function varies. You can create your own loss function, but the W you would be getting would be optimal in that sense, in that loss function sense. You cannot solve for this W. I mean, you cannot solve W for this loss function and you can call it W is optimal in this sense. No, it is optimal in this sense, in this loss function sense. So these are the nuances that you need to pay attention to. Okay, how to solve this? Very simple. Maths looks very difficult. In practice, it looks very simple. So you take X and Y, you would get X and Y, you have a data. So you would get X and Y. You take X and Y. X is the feature matrix. The rows are the feature vectors. Y is a column vector. And sklearn is the scikit-learn. Scikit-learn allows you, so I have imported this module from scikit-learn that does the train test split. So I have taken the 40% of my data set would be the test set, 60% would be the training set. So I have randomly initialized. So where 40% would be going to the test set, X test and Y test, and the 60% would be going to the X train, Y train. Look how we do this, how we solve machine learning with the scikit-learn. The first
Hello, sir.
step, yes. Somebody is asking question. Please go ahead. Please go ahead. What happened? There was a question. Yeah, Shorodipta, maybe if your question is a little bit specific, then I would be able to answer. So in the interest of time, let me move fast. In case of machine learning, so follow this algorithm. I mean, follow these steps. The first step is import the classifier or import the regressor. Here we are regressing, so import the regressor. Second step is initialize the classifier or initialize the regressor. What I did is linear regression. I'm doing linear regression. From linear model, I created this instance. You know, object-oriented programming. You know, initiating an object means from the class. So I am initiating the object, and then there is a method. There is a method written in this class that is fit. That is actually computing W. The W I showed you, that is computing W. I am supplying X train and Y train, and model stores the W. But I don't need model. If you want to print the W and all these things, the parameters, you can use model. Otherwise, I am supplying the X test and it is giving me the Y prediction. And Y prediction need to be compared with the Y test. Y prediction is the estimation, estimated Y hat. This is the Y hat. Wait a minute. So Y prediction need to be, sorry about the disturbance. Y prediction need to be compared with the Y test in order to give us the inaccuracy or how far, how well we are doing. I mean, how far our prediction is from the real target. And the way we can do it by root mean square, there are various mean square error, root mean square error, various way of getting this evaluation. So the last thing is evaluation. First thing is importing the classifier or regressor. Second step is initializing the classifier. Third step is training, where you get the W, you solve for your loss function, you compute the loss function, do either in a closed form or by gradient descent. Most of the time you would be doing gradient descent, because in classifier there is no closed form solution. Regression there may be, but if the data set is too large, you need to go for gradient descent. But you don't care. I mean, you don't need to care. The scikit-learn module will do task for you. If you follow this process, it is easier for you. I mean, this is so simple. And prediction means using the test data to make the prediction, and this is evaluation. Evaluation is important because your advisor, your manager would be interested to know how good is your fit, how good is your machine learning model doing. Okay. Before moving to regression, I would move to uh, no, Shaurad, actually, I would love to get into the discussion, but I don't have time. I need to pace through it. But I'm interested to know about your point. Maybe you can get in touch with me over email or Journal Club, online Journal Club, wherever. There are a lot of options. Uh, Shomonetra Nandi, sir, will this PPT be available later? Yes, of course. Why not? Sir, what is mean by training? What is mean by training? Okay, let me tell you what is meant by training. Training means finding the value of W in a very crude sense. Solving the W, getting W is what you mean training. So a lot of statistics. So what is data science? I showed you data science is the interdisciplinary field that has statistics, computer science, a lot of these things. So there are a lot of things that essentially mean the same thing. What I'm saying, estimating W, computing W is same as training the W. Machine learning the W. I told you, learning what we are learning the values of W. That is training. So in machine learning, so let me be a little bit explicit here. Machine learning has two parts. The first part is in every machine learning task, supervised learning, unsupervised learning, in every machine learning task, the first is computing the W, computing the parameters. That is training. That means in supervised learning, that means establishing the relation between feature matrix X and the target Y. That's how you make the correspondence, make the relation between the feature matrix X and Y by computing the W. That's what is training. That is what is estimation of the W. That means the second part is inference or prediction. When you have done the training or fitting is another term that is also used in statistics. Fitting, model fitting, training, machine learning, they mean the same thing. But when you have computed W, your optimal W, optimal in what sense? Optimal in loss function sense. I am saying it ad nauseum. Do not forget this thing. W cannot be computed out of thin air. When you compute W, you actually minimize the loss function. So W is optimal W. Optimal in what sense? W is optimal in loss function sense. Here the W is optimal in least square sense. So when you get the W, that is called model fitting, training. So scikit-learn has called it fitting. I'm calling it training, same thing. The last stage, not the last stage, the next stage is prediction. With the model computed, the optimal W, I'm predicting on the test X feature, text X feature, মানে X in the test set. I have split it into two parts, training and testing. Why I have split it? Because I would predict on the test part, and I would see how close is my prediction to the ground truth. I mean the target, the test target. And this is the last step. We check this closeness by computing some kind of metric. This is the evaluation part. We check how close this prediction is to the target, the test set target. So this is the evaluation part. So training, testing, these are two parts of a machine learning algorithm. So the program itself forms an equation. Yes, yes. Um, so this is a good question. So program itself finds the equation means it depends on what kind of regressor or classifier you are calling. Linear regression knows what kind of equation it has to solve. Similarly, when I'm moving to logistic regression, that is a classification, it knows what kind of loss function it has to solve. So that's why when I import classifier or regressor, actually under the hood, I'm importing the equation, loss function equation. So moving to classification, so there is another question. Okay. So moving to classification, here things would become a little more interesting. We don't have a value here. We have some discrete observation, faulty or good. Faulty can be represented 0, good can be represented as 1. But how can I, this measure, this XW would give me a column vector of real numbers. How can I make this real number representing good or bad? So these are the real numbers. These can be positive real numbers, fraction, negative fraction, can be anything in the number line. How can they be representing good or bad? Any idea? I'm struggling with this pointer, mouse pointer. Let me get rid of this. Data is not stationary or have multicollinearity. Uh, by multicollinearity, let me know what you understand of multicollinearity. Let me know, and then I would give you some hints, but that cannot be covered in this class. That is out of the scope. If RPM are almost equal, then it's good status. RPM and vibration, they are different. They are different unit, so they cannot be equal, right? So this interrelationship of the columns, that can be studied with there are metrics that help you to study all these things. And in fact, the overfitting, underfitting, they are related to a lot of things are sorry, related to this, and that's why um, it cannot be discussed within 20 minutes or 30 minutes. So, but yeah, there are definitely things that I cannot go into, and but you cannot get into all these fascinating details in the next lecture. Whoever is going to take, whoever is going to teach, you would be discovering all those things. So hold on, hold on. So the classification, but let me know how do you solve the classification problem? Here we have this faulty and good. How these real numbers can be used to represent faulty and good? Any idea? So I've also prepared a notebook for a regression. This is a very simple notebook. The dataset is there in the Boston housing dataset. So if you load this housing dataset, then the columns may represent the criminal record, the age of the neighborhood. There are different columns. I mean, if you take a look at Boston housing, it's widely available. You know the name of the column, what do they mean, crime record, distance from highway, all these things. but the idea is to predict your target variable is to your target variable is the price of the property, price of the land. So that is your target variable, and your target variable is, if I'm not wrong, your target variable is 13th column. 13th column is the median value or something like this. That is the what shall I say, the price of the property. So when I use this kind of thing, perhaps I don't know if you know NumPy yet. If you know NumPy, then it is the all the rows here and the columns are last column is not considered. So from the first column to the last but one column is included. I mean, all 12 columns are included in X, and the 13th column is represented by -1. That is part of Y. So we have X and Y, and the rest you know. Rest I have shown in the slide. So this is how you can solve a regression problem. See, here import the classifier, it's import the regressor. I'm sorry about that. Import the regressor, and someone said, so the regressor would take care of the equation. Yes, regressor knows what kind of loss function you are dealing with. If you change your name, the loss function will change. Inference, okay. So the PPT, where is the PPT? Okay. So the classification, how can we take the classification to represent the faulty and good ones? So far, no response. Okay. So this is what I would employ a technique that is known as one-hot encoding. One-hot encoding, what it means is that converting this kind of discrete values to a probabilistic interpretation. A probabilistic interpretation, you can understand that these are the discrete values, and I don't have ways to represent these discrete values with this continuous number that are appearing anywhere from the number line, right? With these continuous numbers, I cannot represent these discrete values. So the technique I would do is called one-hot encoding. One-hot encoding is how many discrete values are there, faulty and good. There could be another one, for example, faulty, good, in between. So the number of discrete values would be converted to the number of similar columns. So we have two discrete values, faulty and good. So we have two columns, faulty and good. And instead of this what we saw in the regression, we would have probabilistic interpretation. Probability that this machine y1 is the machine is 0 or faulty, or probability that machine is good. 0 is faulty, 1 is good. So if we represent this way, so this I may say that I can represent it as I can represent it as, oops, why it is not working? Maybe I chose the white color for some reason. Yes. So I can assign this as probability 1 because this is faulty. This is faulty. And since it is faulty, the good would be 0. Again, if this is faulty, then I would assign this probability 1 and this would be 0. Those machines which are good, they would get probability 0 and 1, 0 and 1. So if there is a third state, for example, in between, I'm writing in short in between, that step also 1, 0, so they would become 0, 0, 1, this way, 1 and 0, 1 and 0 combination. So this is called one-hot encoding. Perhaps the idea is clear to you. This is called one-hot encoding. Okay. And one-hot encoding means these are the probabilistic interpretations. Probabilistic interpretation means they would lie between 0 and 1. How can we make them lie between 0 and 1? We apply something called sigmoid function or thrashing function. The sigmoid function takes any value from the real number, but it ensures that it stays between 0 and 1. Logistic function or sigmoid function. This is how I am modeling my classification. This is how I'm modeling my classification, that I'm doing XW. So W is unknown, X is known, but this is the beauty of modeling. I am multiplying X with W and transforming those through sigmoid function so that I get the probabilistic values. So this is a simple example here. The sigmoid function, if I model the faulty one minus that would be the good one. So this is the logistic regression model, and we use this kind of modeling to maximize the log likelihood or minimize the cross entropy loss. So what would be the shape of the loss? The shape of, I'm just showing you for your curiosity. Don't let us not go into that. This kind of loss we would be minimizing or maximizing. In case of probabilistic interpretation, we maximize the log likelihood if you go along the probabilistic interpretation. But if you go along the some of the questions I see are a little advanced one, that's why I'm saying to satisfy your curiosity, minimize the I mean, if you think of the optimization, we minimize the cross entropy loss. So this loss is known as negative log likelihood loss, cross entropy loss, logistic loss, log loss. They mean the same thing. So if you minimize this loss, so y is given, so 0 and 1, we know the value. X is given, we are minimizing this loss with respect to w, xw. So xw is hidden in this estimation, y hat. So xw is hidden here. Can you just give me a moment, please? I'm coming. There is a lot of sound here. So so all the losses are they mean the same thing, and y hat have this value xw. W is unknown, so when you minimize this loss, you actually get the optimal value of w. When you have w, that is the training part. When you have w, you can do the prediction. Okay. So let us move to the regression. Yes, this one. Classification. So how do you solve the classification? You solve the classification. Let me see. Using scikit-learn, I am loading the iris dataset. So iris dataset is actually a flower dataset, and it has 4 columns. The 4 columns are the 4 attributes about the petal length, petal width, and sepal length, sepal width. So those of you who know a little bit of botany or biology, they know the specific attributes about the plant leaves or the plant flower. I don't know, plant flower, I guess. Yeah, I'm talking about. So we have 4 columns. That is the idea. For machine learning, we know that we have 4 columns, and we have the target variable. The target variable contains the name of 3 flowers. So there are 3 classes. So earlier we had 2 classes. The machine can be good or bad, but now we have 3 classes. So these 3 classes are are represented in the target variable. So let us see. We have loaded the iris dataset. So iris feature names, I have printed them. So let us see how they look like. So these are the target names. So target names are represented by 0, 1, 2 because I told you there are 3 classes. What are the classes? So this is the target, sorry, target is the 0 and 0, 1, 2. Target names is Setosa, versicolor, virginica. These are the names of the 3 flowers. Feature names. What are the feature names? The column names, sepal length, sepal width, petal length, petal width. So it's 4-dimensional data set. When we talk of dimension, we actually mean the feature matrix. So this is a 4-dimensional data set. And it is very difficult to visualize because we cannot visualize in 4 dimension. How would you classify the data set? Again, like before, we use train test split to do 50%, not 50%, let me do 75. Train size is 75%, 25% is the test set. So X and Y. I guess I need to assign X and Y. I didn't assign X and Y, but so I don't know where Iris has its features. So I don't know how Iris is storing its data. So what I shall do is, like before, so I see the Iris is a class, the object, and I see that Iris has data attribute and target is here. So the next thing is X and Y equal to Iris data and Iris target. Okay, this is how I'm assigning X and Y. And I'm also doing print X dot shape and Y. So X has 150 vectors, 150 observations, and 4 4 columns, so 4-dimensional data. And Y has got 150 elements because Y is a column vector. With this, we would do the train test split. Let us see these. So I said that 75% would go into my training set. So definitely training set is more than the test set. So 112 in the training set, and in test set there are 38 vectors. Like before, I'm importing the classifier. This time I'm calling k nearest neighbor classifier, kind of classifier. I'm initializing the classifier. So knn, k nearest classifier solves a different loss function. I'm initializing the classifier, but the rest of the steps would remain same. I am importing the classifier, I'm initializing the classifier here. I'm training, I mean computing the parameter, classifier's parameter, and then I'm doing prediction. Lastly, I'm doing the evaluation. Evaluation means I'm computing the accuracy score from the test prediction. So if I do that, so accuracy, perhaps accuracy is very good. I mean, near 100% because it's a relatively small and simple data set. But maybe the accuracy would go bad if I give a small amount of data to the training set. Let us see. Yes, accuracy decreased from 1 to 90%. So this way you can play with the data set and understand. Like before, the steps remain same. Importing the classifier, initializing the classifier this way. These are the parameters you are considering. I didn't teach you nearest neighbor, but I did teach you logistic regression. So the classifier I was just showing you, this classifier that I was just showing you, this classifier, it's a logistic regression classifier. So one important point, I am saying logistic regression, but I am saying classifier because logistic regression is actually not a regression. Logistic regression is a classification model. It's a misnomer. It sounds like regression, but definitely, I mean, during interview, people ask this kind of question. What kind of regression logistic regression solves? Logistic regression is not a regressor. Logistic regression doesn't solve regression problem. Logistic regression is actually a classifier. It's a classification model. Okay, never make this mistake. So since I showed you how logistic regression works here, so I must show you how it works in the code. So the way you make logistic regression work is like this. I won't assign x and y again. I have already loaded them. So train test split, test size 20%, so train size 80%. This is how you call logistic regression, like linear regression. You initialize logistic regression this way. You fit, you actually compute W. Here you are computing W. Compute W. You compute W this way. You don't see W. If you want to see W, you need to print it. There is a way to do that. Maybe it's a homework for you. So you, while fitting, you supply X train and Y train. It does the fitting. And once it is ready, you can do the prediction. This object does the prediction this way. This is the prediction, and you do the evaluation with confusion matrix. Confusion matrix, I will tell you what is confusion matrix. In order to tell you what is confusion matrix, I actually try to compare the performance between two kind of classifier. One is logistic regression. There is a multinomial logistic regression. There is another version of logistic regression, that is one versus rest. So I won't go into details. We don't have time. So these are two different classifiers. Within using two different classifiers, you get two different accuracy scores because you are fitting two different models. You would be predicting on, you would be predicting using two models. And so the multinomial logistic regression performed better than one versus rest logistic regression. And this is the confusion matrix. Confusion matrix works this way. This is the predicted label axis. This is the true label axis. So the diagonal ones are the ideal ones. I mean, if you have the diagonal ones populated, that means true label is matching with the predicted level. Any off diagonal score means you are confusing with other. So maybe I did with the multinomial. There should be another logistic regression. Let me plot it. There should be another confusion matrix. Let me plot it. One versus all. So one versus all, perhaps you can see the off diagonal ones. Yes, there is a off diagonal one here. So the predicted label here, 2 is predicted. How shall I do that? 2 is predicted as 1. That is the thing. That's why it has got an entry. So no, 1 is the true level. 1 is predicted as 2. So predicted level is 2, but the true level is 1. This is the true level, and predicted level is 2. So that's why it's a wrong prediction. So that's how the off diagonal, when the off diagonal cells get the values, that means your classifier is losing its accuracy. It's not good for your classifier. The more number of elements in the diagonal ones, that means your predicted level and true level is matching, and your classifier is doing a good job. Okay, So this is how you do I don't want to give you some theory of clustering, because you know how the clustering works. We are grouping. I mean, I guess if you follow the code, you can understand what clustering does. So let us move straight forward to the clustering one. It would be easy if we go to clustering. Just a minute. Maybe it's not working. Import matplot lib pyplot as plt. So I have created this artificial data set. So how many clusters are there? 4 clusters, right? So from visual inspection, I can see there are 4 clusters. So let us cluster them. And the way we can do that is by doing something called k-means clustering. Let me see. Yes, k-means clustering. K-means clustering means we would choose 4 clusters randomly. So let us do this 4 clusters randomly. So one cluster may be this way, one cluster may be this way. Four clusters randomly. One clusters may be this way, and the last cluster, oops, I've taken this right, maybe this way. So once we have, these are the cluster center. So clusters are represented by cluster center. Once we have, then we do a process. We check the association of each point to the closest cluster. I mean, we verify which cluster each point belongs to. So it's a kind of a ownership competition. Each cluster competes for taking as many points as possible, and we make the decision by computing Euclidean distance, just the distance from the clusters. For example, if we consider this point, let me maybe it's not coming. Don't worry. So if we consider this point, this particular point, so its closest cluster center is this. So it would get assigned to this. And this cluster would take mostly this kind, all these points it would take. This cluster would take maybe these points, and this cluster would take maybe these points. This cluster would take maybe these points. Once, this is the first iteration. Once we assign these data points to the respective cluster, we recompute actually, revise. We recompute or revise the cluster center. And we do this by averaging all the data points and represent the cluster center by their average. So let us look at this. If all these points are averaged, then the cluster center would move from this point to this point. If all these points are averaged, then this cluster center would move from this point to this point. And if all these data points are averaged, this cluster center would move from this point to this point. Again, here too, it would move to this. So you see, the cluster center is gradually coming to the true cluster center of these data points. This way, we are doing this in the first iteration. There would be second iteration, there would be third iteration. Gradually, the cluster center would revise itself, and we would start converging to the true cluster center. This is called k-means. What is the drawback of this method? The drawback is we need to know in advance the number of cluster centers. So there are many ways to do that. I won't go into that, but you can maybe this is the homework for you. You can check internet and see how different ways there to compute or to get some sense. There, those are heuristics mostly, but at least you can get some sense of how many clusters should be there. This is one strong motivation to dimensionality reduction, because when there are high dimensional data and we don't know how many clusters are there because you cannot visualize, right? In that case, we do dimensionality reduction, we bring them to 2D or 3D, and we try to check in 2D or 3D how many clusters are there, can there be. And with that information, we go to the original dimension and we try to fit the dataset to see if the fitting is correct. Okay. So once we have all these data points, we apply k-means clustering like before. Here also the same thing. Import the clustering module. Import the clustering module. Initialize the number of clusters. Do the fitting and then do the predicting. Here there is no what shall I say? The y is not there. It's unsupervised, completely unsupervised. So if I do this fitting, it will take some time. K-means usually takes a lot of time because it's iterative in nature and you cannot bypass the loops. So let us see how the clustering look like. So see, we got the correct clusters. The clustering has turned out to be very effective because it's a very simple toy data set, right? So with the 4, we have got this. But what would happen if we do incorrect judgment? I mean, initially, perhaps we don't have proper information and we start with 3 clusters. It's inaccurate. We don't have 3 clusters. We have 4 clusters yet. But let us see what would happen if we fit 3 clusters. So 3 clusters, what it does is that it merge the middle 2 clusters into one. So this is what the 3 clusters does. So if you do underestimate of the number of clusters, you get the clusters, the true clusters getting merged. If you do overestimate, for example, 10, let us overestimate number of clusters, then you would see that the true clusters are getting split up. So they see I mean, uh, the clusters are getting split up into unnecessary distributions. So definitely they don't make sense, right? Dimensionality reduction, our last thing here. Let us load it and answer the questions. Can you explain the test size? Test size, so there is no hard and fast rule to compute the test size. People make different assumption. The way I do is that I usually keep my training size 80% or 75%, so the test size becomes 20% or 25%. In fact, I would recommend something different. So Andrew Ng, in one of his talk, he said something and I like that idea. So you should split your most probably, I mean, uh, he recommended this idea for classification. So let us uh, consider this idea in the context of classification. So the best partitioning would be 60%, 20%, 20%. So 60% is your training set, 20% is your validation set. Validation set is used for determining various hyperparameter and all this kind of stuff. So you won't look at the test set. Whatever testing is done, whatever evaluation is done, you do on the validation set, the 20% of the set. So you train on 60%, you validate on the 20%. Once everything is done and you are very satisfied with your model, only then you actually see the test set once. Only then you go to the test set, the remaining, the last 20%, you compute the model performance on the test set once and just wrap up your experiment and say that with this model, with this modeling approach, I am getting this kind of evaluation score on the 20% test set. So these are the ways you can, it depends on the application, but in most of my research work, um, uh, I have a different interest. I work in areas where the data set size is very small, or you don't have that much data set, or the data set is highly imbalanced. So in my research work, I don't have a lot of data set. I cannot do this kind of splitting, because if I do 20%, 80%, then the 80% is going to be too small. In that case, what we would do is that we do leave one out of cross validation. That means we remove one data point and train on the rest. We remove one data point and train on the rest. And we evaluate on the that particular data point. And then we change the setting. We choose another data point and remove it from the training set and train on the that n-1 data point, and they again test on the held out data point. This way this way of doing evaluation is called leave one out cross validation. There could be careful cross validation, various ways of doing these things. It depends on the application. What happened when a cluster accidentally situated between the cluster equidistant both side? Yes, then you need to break the tie. So it depends on how you are defining the rule. If you define the rule greater than or equal to, then one way of tie breaking would happen. If you define the rule strictly greater then another way of tie breaking would happen. But in my experience, I've seen this kind of edge cases do not matter a lot unless and until you have all the points on the those are the extreme cases, all the points in the bisector of the two data points, some kind of that. Otherwise, these kind of edge cases are for academic interest, but in real life, we don't see these kind of things. Dimensionality reduction, the last thing. So I would start with the dimensional redirection with the IRIS dataset because they are 4 columns, 4 feature vectors, and we cannot visualize the 4 feature vectors, 4 columns. We can visualize till 3 because, as I said, our vision is restricted to 3 dimension. So how we can project from 4 dimension to 3 dimension? Again, the same thing, we call one module that is called PCA. We call PCA and we say that we would choose 3 principal components. Again, this would be totally unknown to you, most of you, if not all. But let us focus on the intuition. Intuition is 3 principal directions. We would project the dataset on 3 principal axes, 3 important axes. Okay. So that's why the parameter is chosen 3 important axes. We have 4 columns, 4 feature vectors, but we would project these feature vectors, feature columns along the 3 important axes. Those axes would be our XYZ. And that way you would be able to visualize this 4-dimensional distribution of the iris dataset, the flower dataset. So let us run this. In fact, I have already executed this. So the 4-dimensional data set, when I project onto the 3 principal axes, 3 important axes, X, Y, Z, those who know principal component, I mean these are the 3 eigenvectors. they carry most of the information. So if we plot them in, I mean, we get the projection in 3 different axes. That's why we get 3 points, XYZ points for each data point. And if we plot the XYZ point, it looks like this. So it shows that two flower classes have quite a bit of overlap, whereas the third flower class is somewhat distant from the rest of the two. This kind of insight you can derive from this kind of visualization, right? So let us go back to the PowerPoint. And what we did is we discussed regression, classification, clustering, and dimensionality reduction, the supervised learning, unsupervised learning, and we have shared the Jupyter notebook. We have covered a little bit of theory, and clustering and dimensionality reduction, they may require a lot of theory. We didn't go to those theories, we don't have time, but we have understood them by invoking our intuition. We have understood them intuitively. I have shown you how the clustering happens in 2D, how the dimensional reduction happens when we project the 4-dimensional data into 3-dimensional figures. So intuitively, we have understood the role of this thing. That's important. But in the subsequent classes, when you would go into more depth, you would have the opportunity to visit the maths and the intricacies of these algorithms. I have a plan to, I mean, gift you one last bit of machine learning beauty that I often find very fascinating. It's a little advanced, but since we spent a lot of time with Python, I thought that I would share with you. It's a little bit advanced, but you would find the connection. I mean, you would enjoy it. Maybe that is the parting note. I would leave it with you to think of that and play with that. But before that, let me see if there is any question. There is indeed a question. So there is a question, how can we make decisions by checking the 3D plot with one perspective? Can the overlapping be different if we see them from different sides? Wonderful question, beautiful question. I really feel like giving a thank you for this question. Let me write thank you. So the answer is, I'm acting lazy. This is definitely the case, and this is the limitation what I have shown you. I should have shown you from a 3D perspective. I didn't do that. Number one reason, I'm acting lazy. The number two reason is that right before starting the meeting, my laptop crashed. So indeed, I thought about it, but I thought, no, let us not get into that because this computational load the visualization would demand may again crash my laptop. So I didn't risk doing that. But definitely that is the limitation of what I showed you. And you should check the 3D visualization. Python has 3D visualization library and view it from different perspective. What I said may not be true in that case, that the overlap that we are seeing may not be kind of good overlap while seeing from different perspective. Maybe the overlap that we are not seeing, that would appear to be a considerable overlapping from some perspective. Definitely true. Thank you for catching this. So before I move into the last part, which is kind of a little bit advanced, but you'd enjoy. So remember, I told you that functions can be treated as objects and functions can be kept in an array. So this is the thing that you can build pipelines, data pipelines with functions. And when you would go into the deep learning stuff, you'd see that the kind of processing, pre-processing we do, normalization, converting it to the tensor, then this and that, all these things are done by series of functions which are kept in an array. Those are actually examples of pipeline, data pipeline. So in this, I showed you a very simple example of building data pipeline. The first of this data pipeline, I'm building a pipeline. So how do I use pipeline? From sklearn pipeline, I import pipeline. And then maybe I do a little bit size enhancement of the fonts. So I import pipeline, and then what I did is this, I create this pipeline. The pipeline takes a list. The list is passed as a this keyword argument, steps. The steps is a list of functions. The first item in the function is scaling, scalar, standard scalar. You scale it to the, I mean, zero mean subtraction and making the each of the columns to 1, normalize them to 1. This is the scaling. So it does the scaling of each columns. This function, if you invoke this object and you put them here, they stay as the first step. The next step is PCA. The next step is PCA. Now, while I'm saying this, that you can keep a function in array, suddenly I can sense one question coming from you, sir. You said that these are the objects, you are invoking the objects. Now, how can you say these are the functions? So yes, I can sense this question. The answer is it's a duality, because everything is object in Python, right? A function is also an object. And later, when you get into the deep learning libraries like PyTorch, you'd see even if you create an object like this, that object can behave as a function because they are callable. It's not that non-functional thing. I'm saying that non-functional thing is callable. There are ways, there are tricks to make an object callable. But the idea is that here everything is object. A function is also object. So if you say that these are not functions, these are objects, true. These are actually objects. Everything in Python is object. I mean, the labels, the annotations, everything is object. So even if I call that it's a function, these are objects. So you may be right if you raise this question, but let us not get into too much of this thing. Let us keep things simple. So the objects, even if we call them objects, so the objects are kept in a list to make a pipeline in order. The order is important. You cannot do PC and then scaling. No, that is not the thing. The first is scaling, then you do PCA. And see, I have used tuple. The first element of the tuple is the naming. I would access them with this naming. Naming is important. Otherwise, I won't be able to differentiate which part is different from the which part is in PCA, which part is in logistic. I won't be able. So the naming is important. I access these steps by this naming. The last one is the logistic regression. That is the classifier. So the first one is the normalization part. The second one is the PCA part, the dimensionality reduction. The last one is the logistic. And you load the digit. After you load the digit, you don't know what would be the number of components. So you do a grid. What would be the number of PCA components? You don't know. Hyperparameters. These are the hyperparameters. Hyperparameters means those parameters are not W. You cannot learn them as part of the machine learning. You need to set them before your before the starting of your algorithm, before the starting of your machine learning task. So since hyperparameters need to be set from domain knowledge, there is another way to set the hyperparameter. So I am showing you how pipeline can help you with setting of the hyperparameters. Since you don't know the components, true number of components in PCA, you set them from 5 to 60, and there is another parameter from logistic regression C. You set it in the log space, -4 to 4. So how I am calling them? So number of components is a parameter in this PCA. PCA has number of components. How I am accessing them? Since I have named as PCA, PCA double underscore name of component would access that component. Logistic double underscore the name of component would access that particular parameter. So this way I set the parameter grid, then I do grid search by passing pipeline through it. I give this X digit and Y digit, and it gives me the best parameter value. And it also shows the PCA variance ratio there. This is something. So we see that maybe 1, 2, 3, 4, 5, 6, 7, 7 and 8 onwards, it gets saturated. So 7 and 8 PCA. So the ideal value would be here, maybe around 10, because we don't need so many values. The PCA variance score shows that it is plateauing towards the higher values. So this is how a pipeline can be created by putting all the different objects, all the different steps into one big list and executing it. Okay, I guess this is our overview of object-oriented programming and our transition to the machine learning overview, a very high-level overview of what the machine learning is, what are the fundamental tasks are, how Python can be used to tackle these fundamental tasks. I hope that with this knowledge, you would be able to make further advancement into your learning journey, because I know there are more in-depth classes in machine learning is going to happen in the next few days. So good luck. If you have any question, please let me know. Otherwise, we would be wrapping it up. Yes, sure. I didn't do that. I apologize for the last class. I thought I would do the sharing of the course materials in one go, and I'm going to do that. Sorry about that. Yes, I'm going to share all the lecture materials on Google Classroom. So there are two requests, Himadri and also Kabir Mohammed. They are asking me to share the lecture materials. Definitely. And again, I'm very sorry I didn't do that for the last class. I'm going to do it for both of the classes. Yes, somebody asked me, could you share your email? So let me show you my email. Mm, this is my email. This is my email. And also, if you remember, we have this online journal club where you can send me direct message if email is not your stuff, if you are more of a direct message person, then you can contact me on the online journal club. You have the link. You can contact me there too. And also Google Classroom, you can post your question and I will be answering there And last few days, I mean, the weekend was actually very hectic for me. I couldn't upload the materials, but I'm going to do it today. Okay, nice sharing ideas with all of you. It was a very enjoyable session for me, and I have learned a lot from your interaction with you and while answering your question. Thank you for your time. Good night. Bye.